Hi, and welcome to the section on 3.5 Graphing Techniques and Transformations. I just want to let you guys know that I decided to video this first by doing all the writing portion first, and I'm actually narrating this afterwards. I actually increased the speed to this video because this video is so long, because I wanted to shorten the length, because I know you guys won't watch something if it's too long. So everything you see here in this top portion, I already started writing it out ahead of time because you guys should know this already, all the basic functions that you should have memorized already. And what I'm doing here is I'm just graphing one of those basic functions. I just picked one at random and decided to graph it so we could use it for the next example on vertical shifts. I decided to use p of x is equal to the absolute value of x. And the only reason I decided to call this p of x is because another way that I like to call the basic functions, or I like to call them parent functions. And so p, that's the first letter in the word parent, so that's why I called it p of x. So everything you see that I'm writing out here, the domain, the range, the graph, the way I labeled the points, none of this should be new to anybody here in my class. Everyone should know that, yes, this is the way I like to see things written out. Okay, so here, let's get into the actual new portion of this section is the vertical shifts. And I'm going to actually be referring to this one particular parent function that I just finished drawing here. So a vertical shift. So it says here, if a positive real number k is added to the output of the function y equal to f of x, the graph of the new function y equal to f of x plus k is the graph of f shifted vertically up k units. And if we're subtracting k, then it's just going to shift our function down k units. So let's refer back to our parent function, p of x is equal to the absolute value of x. And what I'm going to do is I'm going to transform this function by subtracting 3 to it. I'm going to call this f of x. Since I'm subtracting 3 to the absolute value of x, I'm transforming the parent function, because what I'm actually going to do to that parent function is I'm going to shift p of x equal to the absolute value of x down 3 units. So that's what I'm going to do to it. What I'm going to do over here is I'm going to graph the parent function so we can compare the two functions and see how this transformation actually, took place. So let me do the parent function in a different color so it kind of shows up a little bit easier. I'm going to use a light blue for my parent function. And let's go ahead and make some points here. We already know these points because I just finished graphing this in the last little graph that I did for you guys. So there's our parent function. I'm going to label my points because that might make it easier for me to figure out what my new points of my new function are going to be. And I'm going to label my function, my parent function. Now, what I'm going to do is each one of these points is going to be shifted down 3 units. So this vertex here at the origin, down 3 units. This point here at 1, 1, that's going to go down 3 units as well. And the point 2, 2 is going to go down 3 units, and so on. All of these points are going down 3 units. And there is our new function. So you see, this new function is a transformation of our old function here. It's kind of like, a parent, That's why I like to call it the parent function. A parent has like a child, and the child kind of looks like the parent, but it was kind of changed a little bit, Child looks different maybe in some ways, but looks something like your parent. Well, this is what happened here to this function. It looks something like the parent function, but instead of being, with the vertex at the origin, it's got shifted down 3 units. Everything is down 3 units there. Okay, so now I'm labeling the points for our new function here. Everybody knows that when I do graphs, I like the points that you use in your graph to be nicely labeled, neatly labeled there. I like you to extend your function all the way to the ends of the graph. If there's arrows on the ends of those, whatever you're working with here, you draw arrows. And it always looks nice when you label the function with its equation. The domain for this is going to be all the reals, and the range is going to be the half-closed interval from -3 to infinity. Or another way to say this is the set of all y such that y is greater than or equal to -3. Sorry about that. All right, let's go on to the next example here. All right, now we're ready to focus on horizontal shifts. So this is going to mean that we're taking basically our parent graph and we're going to shift it to the sides, either to the left or to the right. So here for the first one, it says if the argument x of a function f is replaced by x minus h, h is greater than 0, the graph of the new function y equal to f of quantity x minus h is the graph of f shifted horizontally right h units. So what I like to do is I like to take that part that says like that x minus h part, that part that's going to be within the function, I like to set it equal to 0, and I like to solve for x to figure out which way I'm going. So this one I can tell that by solving for x there, I got x is equal to positive h. So that tells me I'm going to the positive x direction to the right, and I'm going to be going to the right h units. And I can do the same thing if I've got x plus h, where h is greater than 0, right? And if I have x plus h, where h is greater than 0, then that means I'm going to be shifting to the left h units. So that's basically what it means. All right, this time we're going to use a different p of x. We're going to use our parent function is going to be p of x is equal to x squared. So we have a little bit of variety. And let's have our f of x function be equal to x minus 3 quantity squared. So I'm going to take what's inside the parentheses. I'm going to set that equal to 0, and I'm going to solve it. That's going to help me figure out which way I need to go. So if I solve this for x, I'm going to get x is equal to a positive 3. Because it's a positive 3, I know that if I want to go in the positive direction, I'm going to have to move to the right. So this is basically telling me that I'm shifting my parent graph, right, 3 units to the right, to the positive side. That's what it means. Okay, so we're going to shift p of x is equal to x squared 3 units to the right. All right, let's go ahead and graph this. So why don't we graph our parent graph? I'm going to use a pretty light blue color to graph my parent graph. And that's going to be centered at the origin right here, right at the y-axis. So the parent graph, hopefully you guys already know how to graph a basic parabola or basic quadratic function. But maybe we should review that just a little bit just in case. Remember, we go over 1, up 1, over 2, up 4. That's the pattern, all right? Why is that? Because we're squaring those x values. So when you square 1, you get 1. When you square 2, you get 4. That's why we're going up 4 when you go over 2. Let's go ahead and label these points. Now that I labeled them, we're ready to go ahead and graph our transformation. So we have transformed our parent graph by shifting this to the right 3 units. Every point is going to be shifted to the right. So I'm going to start off here with the vertex. And then I'm going to do this point here that was at 1, 1 over 3 units. And then this point here at 2, 4 over 3 units. And there goes, that's half of our parabola. And let me label those points before I forget them. So now that's going to be 5, 4. I'm just adding 3 to the x value of the parent graph points. And the next one here down is 4, 1. And then the vertex, which was at 0, 0, is now at 3, 0. Let me erase some of these arrows so I have space to draw the left-hand side of this parabola. Now I'm going to shift this point over 3 units, and lastly this point over 3 units. Now I can complete my parabola. There it is. And now I can label all of those points. So we basically transformed our parent graph by just shifting it to the right 3 units. The domain. So the domain of this parabola, or this function, this quadratic function, is going to be all the reals. The range is going to be, that one's going to be a little bit different from that one, right? It's not all the reals. It's going to be not open here, but it should be the half-closed interval from 0 to infinity. Or we could also write that as the set of all y, such that y is greater than or equal to 0. And there we go. And that's our horizontal shift. Let's do an example here of a vertical compression. So if a function y equal to f of x is multiplied by a positive number a, then the graph of the new function y equal to a times f of x is obtained by multiplying each y coordinate of the graph of y equal to f of x by a. Let's do vertical compression first. So let's use p of x is equal to x squared, and I'm going to do f of x is equal to 1/2 x squared. Since the a value is 1/2, 1/2 is a value that is greater than 0 and less than 1. Therefore, it falls into this category of vertical compression. So imagine when you hear vertical compression, I'm taking my original, parabola from that basic function, and I'm squashing it down vertically. That's what it means to be vertically compressed. It's getting like squashed. If you need to write that in your notes because that's going to help you remember, write that down right now. It's getting squashed. All right, so the graph of p of x is equal to x squared will be vertically compressed by a factor of 1/2. That's the mathematically correct way of saying that. We don't say it's getting squashed, but when people write stuff like that on tests, I like it because it means they understand, kind of like what's happening. But this should be the correct way of phrasing that. Let's go ahead and draw our parent function first. And then after we draw our parent function, we are going to draw our new transformed function here to see the comparison, to make the comparison between the two. So there's my parent function, right? Everyone should know the graph of that basic parabola right there. Over 1, up 1, over 2, up 4 on each side. It's symmetrical, right? Across the y-axis, this is an even function. So it's going to have symmetry there. There is an imaginary axis of symmetry going right down the y-axis for this function. So before I go ahead and draw that new function, let's go ahead and actually multiply each one of the y coordinates by that factor of a. So here are the coordinates of the parent function. I'm going to multiply each one of the y values there in my table of values by a 1/2, and we'll see what values we get now to help us graph our new transformed function. So my new f of x values are going to be these. 2, 1/2, 0, 1/2, and 2. All right, now that we've got our new y values, let's go ahead and graph these. Let's plot those points. So I've got one here at 0, 0. I got here one at 1.5. And then I've got here one at 2, 2, negative 1.5. And then I've got negative 2, 2. So this parabola looks like it's a little bit wider than the other parabola, than the parent function, right? It looks like it got squashed a little bit down, right? That means it was vertically compressed. Let's go ahead and label our function with the equation. This is f of x is equal to 1/2 x squared, And let's go ahead and label our ordered pairs. So this is 2 comma 2, 1 comma 1, I'm sorry, 1 comma 1 half, 0 comma 0, negative 1 comma 1, and negative 2 comma 2. Yes. So there we go. What's the domain? Domain is going to be all of the reals. The open interval from negative infinity to infinity, or the set of all x such that x is an element of the set of real numbers. And the range. The range is going to be the half-closed interval from 0 to infinity, or the set of all y such that y is greater than or equal to 0. So that would be our domain and range for our f of x function, right? Not our parent one, because we're focusing right now on the transformations. All right, we're ready to go on here to a vertical stretch. So if a vertical compression means it's getting kind of like squashed down, a vertical stretch means it's, imagine I'm pulling it up, right? Or pulling up and down, right? So instead of getting wider, the parabola is going to get more narrow, right? If we're working with p of x is equal to, in this case, x squared. And I am, just to keep it easier for us, because I think a lot of people like this function. They feel familiar with it. That's why I'm choosing to use it a lot, so that people get really, they feel more like they understand what is the transformation about, you know. And then I think it's easier to transfer that information with all the other basic functions, like our cubic and our square root and our reciprocal function. All right, so if we've got f of x is equal to 2x squared, our a in this case is going to be equal to 2. Looking back over here at our definition here, it says if a is greater than 1, then a vertical stretch by a factor of a results. So our a is equal to 2, therefore it is greater than 1, so we have a vertical stretch by a factor of a occurring here. That's what's going on. Okay, so let's go ahead and write down here what is the transformation. P of x equal to x squared will be vertically stretched by a factor of 2. So now what I'm going to do here first, I want to make sure I have enough little marks here to graph both of these on here. But first I'm going to graph the parent function, so we can do a comparison of the two functions. There's our parent function. Now I'm going to graph our function that has been transformed, right? So I'm going to graph next. Oh, I didn't close that ordered pair. Let me go back and close that last ordered pair right there. Perfect, right? It's all about the notation. It's all about the notation. You guys are very careful about those details. All right, so here I'm going to take each one of the y values in my parent function, and I'm going to multiply them by a factor of 2. All right, so let's go ahead and do that. I'm just going to leave that 0, 0 alone because it's already going to stay at the origin, because 0 times 2, it's going to stay 0, 0. The other ones are going to change. So here we go. We've got p of x, our parent function. Y values were 4, 1, 0, 1, and 4. Let's multiply by a factor of 2 to each one of those coordinates, those y coordinates. And we're going to end up with an 8, a 2, a 0, a 2, an 8. All right. Let's go ahead and plot those points. So those points, coming over here, 0, 0, we said that one, right, would stay right where it's at because 0 times 2 is 0, so that's not going to change. And then we've got that 1 comma 2, we've got that 2 comma 8, and they got that negative 1 comma 2, and we got that negative 2 comma 8. So if you look at this parabola looks like it's a little more narrow than the original parent function. Another way of saying, that's more narrow is we can say that it was vertically stretched by a factor of 2. All right? Let's go ahead and label these ordered pairs. Remember that everything that I'm doing here for you guys, I'm modeling for you guys, the type of behavior that you guys should continue in all of your math classes, because this is what your professors like to see. And teachers, everyone out there, they like to see this kind of stuff. All right, let's go ahead and move on. I didn't write down the domain and range for that one, but you guys should know the domain is going to be all of the reals, and the range is the half-closed interval from 0 to infinity. All right, horizontal compression or stretch. If the argument of a function y equal to f of x is multiplied by a positive number a, then the graph of a new function y equal to f of ax is obtained by multiplying each x coordinate of the graph of y equal to f of x by 1 over a. So let's say our p of x is equal to x squared, f of x is equal to 2x, and that whole thing is going to get squared. Now, I just want to mention that f of x is equal to this 2x, all of this being squared, is the same as 2x times 2x, which is equal to 4x squared. If we were to write it this way, based off of what we just learned, this means that f of x is equal to 4x squared, which would represent the same thing as a vertical stretch, right? It would represent that the parent function is being vertically stretched by a factor of 4. That's what it means. So it's just another way of thinking about it. Sometimes it helps to rewrite things just to help us understand what we're doing. So remember that all of this stuff, in one way or another, it's connected to, something else you've learned. So this, even though it's talking about something called a horizontal compression, we can also think of it in terms of a vertical stretch. Now, if we want to think of it in terms of a horizontal compression, the factor that it's being horizontally compressed by is going to be different than the factor it's being vertically stretched by. I know that was a lot, right? So let's take this one step at a time. So the a in this case is the 2, right? We're not thinking about multiplying it out to get the vertical stretch factor, right? We're thinking about this in terms of a horizontal compression. So right now, before we square it, that a is a 2 in this case. Since the a is greater than 1, this is going to be considered a horizontal compression. And it's going to be horizontally compressed by a factor of 1 over a. In this case, it's 1 over 2. So let's go ahead and write that out so that it makes more sense to us. Remember, the more times you write something out, the more times you say it out loud, the easier it's going to get for us and the more it's going to make sense. P of x is equal to x squared will be horizontally compressed by a factor of 1/2. So in the last one, where we're talking about vertical stretch, you are multiplying y values, right? And for this one, you would have multiplied the y values by 4. But in this one, we're going to multiply the x values, or the x coordinates of the parent graph, by 1/2. And you're going to notice that if you do this, It's going to give you the same graph if you would have multiplied the y values by a 4. So let's go ahead and do this. Let's write down the values, our coordinates for our parent graph. Looking at the x coordinates, let's multiply each one of those by a half. So this is going to be -2 times a half, -1 times a half, 0 times a half, 1 times a half, and 2 times a half. That's going to give us our new x values. Our new x values are going to end up being -1, -1/2, 0, 1/2, 1. Our f of x, or our y values, are going to remain the same as the parent graph. Those are not going to change. Let's go ahead and plot those points. Let's go see what that graph looks like. Before I plot my f of x, let's go ahead and plot our parent function first so that we can make the comparison before I do these new ordered pairs that I came up with, right? So let's use my pretty light blue color here. And remember that our parent graph, the pattern is we start off here at the vertex, and when we start off at the vertex, we're going to go over 1, up 1, over 2, up 4. There is our lovely parent function. Let's use a different color for our f of x function, our function that is being transformed. So we've got -1, 4, we've got -1/2, 1, 0, 0, 1/2, 1, and 1, 4. And if you look at it, this looks like this function was horizontally compressed. This time it got squashed from the sides. Imagine you took your hands and you went to that parent function, you just kind of squashed it from the sides to make it look more narrow. Another way to think of it is you could also think of it as being vertically stretched by a factor of 4. So if you look at the y value, 1, 4, that's over 1, up 1, right? Well, I made a mistake there. Let me fix that first. Yes, there we go. 1, 4, that's what I meant. So if you look at the y values, it's over 1, up 4. That means it's being vertically stretched by a factor of 4. Or if you're thinking it in terms of horizontal compression, the x values of the parent graph got multiplied by a factor of 1/2. So you can think of it either way. So we're going to say here that this was a horizontal compression by a factor of 1/2. And this is the same as thinking of this as a vertical stretch by a factor of 4. Funny how I sped up the speed of my writing video and I still got like time to stop and think, and I don't have to talk throughout the whole thing. I guess I didn't speed it up fast enough. Alright, horizontal stretch. Since a horizontal compression meant we're squashing it in from the sides, a horizontal stretch means we're going to be stretching it out to the sides, to the left and to the right. So in this case, we're going to look at the same parent function because I think it's easy to kind of figure out the idea when we're working with something like this parent function. This p of x is equal to x squared, because you guys are so familiar with that function, and we're going to use f of x is equal to 1/2 x, and all of that's getting squared. So in this case, we're looking at the situation here where a is greater than 0 and a is less than 1. It's going to result in a horizontal stretch by a factor of 1 over a. That's what's going to happen here. So if a is greater than 0 and less than 1, a horizontal stretch by a factor of 1 over a results. Okay, once again, reminder, we're multiplying the x coordinate by 1 over a. And I just want to remind you that, once again, if you wanted to multiply this out and multiply 1/2 x times 1/2 x and get 1/4 x, you could also say that this is being vertically compressed by a factor of 1/4, since 1/2 times 1/2 is 1/4. But once again, we're thinking of this in terms of a horizontal stretch, so I'm not going to think of it that way. I'm going to write here a is equal to 1 over 2. I want 1 over a, so that would be 1 over 1/2. When I divide by fractions, I multiply by the reciprocal, so that's going to turn into 2. So the factor that I'm going to multiply my x coordinates by is going to be a 2. That's the factor it's going to get horizontally stretched by. P of x equal to x squared will be horizontally stretched by a factor of 2. All right. So let's go ahead and come up with a table of values here. Oh no, let's not do a table of values. I was just kidding. I meant, let's go ahead and actually multiply this out so I could also show you that this could also be represented as a vertical compression. So if we multiply it out this way and we get 1/4 x squared, this would be, we could describe this transformation as being vertically compressed by a factor of 1/4. Okay, let's go on. Yes, let's just do something here. Okay, these are the same, right? When you say something is being horizontally stretched by a factor of 2, or whether you say it's being vertically compressed by a factor of 1/4, it means the same thing. One is affecting, right? Once again, we said the x values, one is affecting the y values. Let's go ahead and draw our parent graph first so that we can see the comparison between them. There's our parent graph. P of x is equal to x squared in pretty light blue. Now let's use another color to represent our f of x function. All right, so this time I'm going to go ahead and have to come up with these points. Amazing how long it takes me to do this. It's amazing. All right, I'm going to multiply all of the x values by 2. Yes, I might have mentioned that already, but it's always good to repeat things because that's the way we learn, right? We learn through our repetition. So if I multiply the x value here, my x coordinate here, the -2 by 2, I get -4. The y value stays the same, so it's going to be at -4, 4. If I multiply the next x value by 2, -1 times 2, that's going to give me a -2. The y value stays the same, so it's going to be at 1. So it'll be -2, 1. 0, well, 0 times 2 is just going to give me a 0, so that's not going to go anywhere. So we're going to keep that right there at the origin. All right, let's go over here. There we've got a 2, 4, and if I multiply 2 by 2, it's going to give me 4, 4. And there was 1, 1. If I multiply 1 by 2, it's going to give me 2, 1. And then there's our origin. let's go ahead and connect the points. So you guys can tell by looking at this that it looks like this parabola was stretched, right? Horizontally, it was stretched to the sides. You could also think of it as a vertical compression. And I just want to remind you that you could always plug these into your graphing calculator, right? To check these. So you can always plug in, you know, your parent graph, and then you could plug in, you know, your transformation to take the f of x is equal to 1/2 x, and then make sure you put parentheses around that whole thing and then square it, and to make sure and to double check your work there. Reflection about the x-axis. When you say reflection about the x-axis, it means the same thing as reflection across the x-axis. If that makes you feel a little bit better, then you guys can definitely go ahead and, you know, cross out the word about and write down the word across. Whatever helps you understand it better. When a function is multiplied by -1, the graph of the new function y equal to negative f of x is the reflection about the x-axis, or across the x-axis of the graph of the function f. Why don't we use p of x is equal to x squared, just because we're, you know, I know I've been doing almost all these problems with this one, but I feel like it's the function that you guys are the most familiar with, and when I do all these transformations, it's the one it's going to help you remember the transformations. It'll probably be the easier one that's going to help you remember the transformations. And then when you apply them to the other ones, since you have this easier function, you know, to relate to, it's going to be easier for you guys to get to learn that idea and to remember it. That's what I think. So yeah, let's go ahead and do this. So I see there's a negative being multiplied in front of the x squared. When I see a negative in front of there, I say, oh, since I have a negative that's being multiplied to my f of x, or to my p of x, to the parent function, that means that the p of x will be reflected about the x-axis, or across the x-axis. So we're going to go ahead and graph our parent function in that pretty light blue color, because it's so pretty with that color. I love it. So once again, I'm just quickly drawing the points because I know where those are at. Over 1, up 1, over 2, up 4. Just so you can compare to the parent function. But these should be like, you know, it should be second nature to you guys. You guys should know these already by heart, like the back of your hand. All of those basic functions, you should be able to graph them without a table of values. You should have points that just pop up to into your mind that you're like, yes, these are the right points in order to help me graph this. And then in order to reflect it about the x-axis, I'm just going to have to basically multiply all of the y values by a negative, by -1. And there we go. There is our reflection. Questions, or I want to say questions, but I know you guys can't ask questions, but if you guys have questions on any of these, just let me know. I can answer them. I didn't write down the domain and range for that one, but you guys know the domain for that is all the reals. The range is going to be the half open interval from -infinity to 0. I made a mistake on this one, so I'm just fixing it there. That's supposed to be reflection about the y-axis. It said x-axis, but we just did the x-axis, so it wouldn't make sense to do the same example twice. So once again, p of x is equal to, oh yeah, you know what, let's use a different parent function for this one. Let's use p of x is equal to the square root of x. You know why I want to use a different one? Because if I use p of x is equal to x squared, that function is an even function and it is symmetrical across the y-axis already. So if I were to reflect it across the y-axis, you wouldn't be able to tell the difference. But if I use this one, p of x is equal to the square root of x, you will be able to tell the difference. You'll be able to see the symmetry, which is nice. So let's use f of x is equal to the square root of negative x. Now I know some of you are thinking, wait a minute, you put a negative inside of a square root, you know? Can you do that? And I'm like, yes, you can, because it's an x, and as long as I choose values in my domain that will change that negative to a positive, I'll be okay. So let's figure out which are those values. I'm going to take negative x, my radicand, and set it greater than or equal to 0 and solve. Let's divide both sides by -1. We're going to invert the inequality, and we get x is less than or equal to 0. So in order for me to be able to choose values that are defined for this function, I'm going to have to choose values that are less than or equal to 0. So those are values that are going to be negative values or the number 0. Or in other words, I guess we could say non-positive values. Yeah, does that make sense? Yes, I think it does. All right, let's choose values like that. Let's choose 0, let's choose -1, and let's choose -4. Let's plug those in and let's see what we get. Actually, first, let's graph our parent function with my pretty light blue color, because otherwise we won't be able to see the reflection. So I just quickly graphed my parent function. You guys, once again, you guys should know how to graph every one of these parent functions already. So I just went through it quickly. Once you can double check it on your graphing calculator if you're not sure, but I just sketched it out real fast. The domain of my parent function, the p of x is equal to the square root of x, is going to be the half closed interval from 0 to infinity, or the set of all x such that x is greater than or equal to 0. So notice that that domain was different from my other domain. And the range is going to be, it's going to be almost the same thing right here, right? So except when I write in set builder, I'll say the set of all y. The set of all y such that y is greater than or equal to 0. All right, now let's go ahead and graph our f of x, or our function that's being transformed. So if I plug in these values, if I plug in 0, I get 0. If I plug in -1, I get 1. And if I plug in -4, I'm going to get, that's not right. That's not 4. Please let me fix that right now. Please let me catch that I made a mistake right there. Please let me catch it. Please come. No. What? No. 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 I made a mistake. Let's go back. Fix it. Fix it. Fix it. So I made a mistake right here where the f of x is equal to 4. I was writing too quickly, or I was tired when I was doing this, but that should say -4, comma 2 for that particular ordered pair. That's what it should say. So you guys fix it on your notes. I'm sure I'm going to catch it right now. I'm sure I'm going to catch it, because that would be just incredibly embarrassing if I didn't catch that. It's -4, comma 2. There you go. There you go. Good job. So I fixed it. Thank goodness I caught it. And we're able to now move on. Let's label our ordered pairs. Good. And now this is a nice picture of this graph here, because you can actually see the symmetry across the y-axis. You can actually see that reflection occurring across the y-axis. Good. All right, let's go ahead and do these problems. Write the function whose graph is the graph of y equal to x cubed, but is shifted to the left 4 units. So to shift to the left, we're going to have to write, remember, the opposite, x plus 4, and then that's going to be quantity cubed. Remember, when you're shifting to the left or to the right, you're going to have to remember to think in terms of like the opposite sign to go into the correct direction. Shifted down 4 units. So this one, we're going to make sure we do not put any parentheses in this case, and we're just going to write x cubed and then that minus 4. This one, you don't think opposite when it goes up or down. You just go ahead and write, if it's down, it's minus. If it's up, it's a plus. Reflection about the x-axis. So reflection about the x-axis, that's going to be f of x is equal to negative x cubed, and horizontally stretched by a factor of 4. This is probably the one that's going to be a little bit tricky, because remember when we do horizontal stretches or horizontal compressions, we have to remember that 1 over a part. So 1 over a is equal to 4. So if I solved for a here, this is going to give me a is equal to 1/4, right? So everyone should know how to solve that rational equation right there. If you solve for a, everyone should already know how to do that. We talked about doing that at the beginning of the semester, so review that in your notes in case you don't remember. So this is going to be f of x is equal to 1/4 x, and that's all going to get cubed. Good. Find the function that is finally graphed after each of the following transformations are applied to the graph of y equal to the square root of x. Reflect about the x-axis. Okay, so this is some of the stuff we already did this here, right? So we're going to write f of x is equal to the negative square root of x. That's going to be a reflection about the x-axis. Shift right 3 units. When you shift right or to the left, that's when you have to think in terms of the opposite sign. So I'm going to write f of x is equal to, and this is going to be the entire square root of x minus 3. All right, remember, we're going to move to the right, we're going to the positive x direction. You got to think in terms of the opposite sign. So the opposite of a plus, it's going to be a minus. So you got to remember to put x minus 3. If you don't trust me, go ahead and plot that into your graphing calculator, or put that into your graphing calculator and see what you get. And the last one, shift down 2 units, we're just going to subtract 2. And that subtraction of 2 has to be outside of the square root. All right, number 6. Suppose that the x-intercepts of the graph y equal to f of x are equal to negative 5, 0, and 3, 0. What are the x-intercepts of the graph of y equal to f of x y equal to f of x plus 2? So we're going to have to add 2 here. We're thinking in terms of adding 2 to the x, but because it's inside the parentheses, remember we're thinking in terms of opposites. So we're actually going to be subtracting 2 or moving to the, more to the left here. So if I subtract 2 to my x values, because the x values are the one that determines whether you go left or right, what is negative 5 minus 2 going to give me? That's going to give me my first x coordinate, negative 7, 0. And then 3 minus 2, that's going to be 1, 0. What are the x-intercepts of the graph y equal to f of x minus 2? We're going to think in terms of opposite, right? The opposite of x minus 2, we're going to think plus. We're going to move to the right. So I'm going to add 2 to my x values in those ordered pairs. And that's going to give me my new x-intercepts. That's going to give me negative 3, 0, and 5, 0. Okay, for this next problem C, what are the x-intercepts of the graph y equal to 4 times f of x? So 4 times f of x, we're going to multiply the y values by a factor of 4. So if I were to multiply the y values in those x-intercepts, they happen to be zeros, the y values. So when you multiply 0 times anything, it's going to remain a 0. So 0 times 4, that's just going to be a 0. And then for the other x-intercept, for that 3, 0, we're going to have 0 times 4, which is going to remain 0. So our x-intercepts will be negative 5, 0, and 3, 0. Yes, those are our x-intercepts. D, what are the x-intercepts? Oh, I forgot the box in B. Let's box that in. All right, D, what are the x-intercepts of the graph of y equal to f of negative x? So negative x, when you are substituting that negative x in there, let's recall what that means. What does that mean? Oh, here it is. F of negative x. It's the reflection about the y-axis. So look at what happens to the x values when you reflect across the y-axis. They change to the opposite sign. So it's like we multiplied by a negative 1 to the x values. So that's exactly what we're going to do here. We're going to multiply the x values by a negative. So it's going to be negative 5 times negative 1, comma 0, and it's going to be 3 times negative 1, comma 0. So my new x-intercepts will be 5, comma 0 and negative 3, comma 0. Yes, box that in. And now we're ready to do our graphing portion, number 7 and number 8. Graph each function using transformation techniques. Start with the graph of the basic function and show all stages. Show at least 3 key points. Find the domain and range of each function. It says show at least 3 key points, but when you're working with something like a parabola or a cubic, I think it's better to show at least 5 points. I would only show 3 like if I were working with something like a square root function, but like a lot of these other functions, I would use 5. Now here I wrote down the general form for a quadratic for when you're trying to figure out transformations. F of x is equal to a times the quantity x minus h, quantity squared plus k. The vertex is going to always end up being your h comma k value, or sometimes people like to call that like the locator point. So I'm going to take the inside of the parentheses, set it equal to 0, and solve for x. That's going to give me x is equal to a negative 3. It's also telling me that I'm shifting my parent graph to the left 3 units. The minus 5 at the end over here, that's my k value. So my vertex is going to be negative 3, comma negative 5. That negative 5 also says that I'm shifting my parent graph down 5 units. And then the 2 at the very front means that I'm going to be vertically stretching this graph. That's my a. So I'm going to be vertically stretching it by a factor of 2. Since my a is greater than 1. So that's what it means. So let's write that down. It's going to be vertically stretched. It's going to vertically stretch p of x is equal to x squared by a factor of 2. Because we are vertically stretching this by a factor of 2, we're going to multiply our y values in the parent graph by 2. Y values, remember that determines how much you go up by, right? The rise. So it's kind of like a way to help you remember there. It's the y values when you're vertically stretching it. Okay, so I started drawing over here to the right. I started drawing the parent function just to help us when we're drawing our new transform function, because we're talking about the y values and the change that's occurring to the y values. So in the parent function, remember, we go over 1, up 1, over 2, up 4. So it's that pattern that I'm going to want to use here to help me come up with these points. Now, instead of going over 1, up 1, I'm going to be going over 1, up 2, because I need to multiply the y values by a 2. And when I go over 2, I'm going to want to go up, not 4, but what's 4 times 2? 4 times 2 is 8. So I'm going to go over 2, up 8. It's going to be 8 units that we're going to be going up by. And I should land right here where y is equal to 3, right? The distance here, it should, between like the two y values that I have to see here, like from negative 5 to 3 should be 8 units. So 3 minus a negative 5, it's 8. So yes, that's the correct spot. And there's got to be symmetry on the opposite side, because there is an imaginary axis of symmetry in this parabola. So whatever you have on one side of the parabola, you got to have the mirror image on the other side. So this is our parabola right here. So I would describe this parabola, once again, as being, it's being vertically stretched by a factor of 2. It's also being horizontally shifted 3 units to the left, and it's being vertically shifted 5 units down. So that's how I would describe this parabola. I apologize there. I'm a little bit of a perfectionist. I'm trying to make it look perfect. The domain would be all the reals. The range would be the half-closed interval from -5 to infinity, or the set of all y such that y is greater than or equal to -5. So that would be the domain and range. Let me go ahead and label the function with the equation. And then we make some space there so I can write down the domain and range. All the reals, or the open interval from -infinity to +infinity, or the set of all x such that x is an element of the set of real numbers. And the range is going to be the half-closed interval from -5 to infinity, or we could also write that in set builder notation, the set of all y such that y is greater than or equal to -5. All right, that was a nice little graph there. Let's go ahead and graph this next function. H of x is equal to the cube root of x minus 1. And then we're adding 3 at the end of it. There is no vertical or horizontal like compression or stretch occurring here. There is only a vertical and horizontal shift. So let's first find that inside part here, and this is not only going to help us here also for finding the horizontal shift. This can also help you for finding the domain, right? So our locator point here for this cube root function, I'm first going to have to take that inside of the cube root and set it equal to 0 and solve for x. I get a +1, so that's going to be my x value to 1 and 3. Or another way to think of this function is going to be shifted 1 unit to the right and 3 units up. So there's going to be a vertical shift of 3 units, and there is going to be a horizontal shift of 1 unit to the right. And I forgot to say there's a vertical shift that's going up 3 units, so I wrote that in right now, vertical shift up of 3 units. Okay, we can go ahead and graph this now. We are almost done with this handout. You guys all deserve a cookie. You guys all deserve a round of applause for making it through to the end of this video. Congratulations. Well, this is about the time our class normally lasts anyways, but it shouldn't, but I think it's harder to watch a video instead of coming to a class, having a live class to go to. So, congratulations. Anyways. Okay, so let's go ahead and graph our parent function first. I'm going to use my pretty light blue to graph my parent function first. I was graphing my locator point to start graphing the actual function, but I actually graphed the parent one so you guys can compare them, right? Because I did a little graph of the parent one for that top one. So here's my parent one. I'm going to use the ordered pairs here. Which ordered pairs did I use? So it looks like I substituted here into this. I used -2, I used -1, I used, I used -8, I used -1, I used 0, I used 1, and I used 8 to plug into my, for my parent function. I don't know why I didn't write those in the table of values up there, but the x values for the parent one were -8, -1, 0, 1, and 8. And then when you take the cube root of those, you get the y values of -2, -1, 0, 1, and then 2. And then we basically take all of those points and we just shift them all up 3 units, and then to the right 1 unit. And we come up with our values right here. So the locator point's the easy one to find, right? And then if you've got those other points of the parent function, you could just basically add 3 to the y value and then add 1 to the x value. And that'll get you all your new values for your transformed function. Yeah, so I think that's about it. I'm just going to finish labeling these points here. And once again, I really want to encourage you guys to be using your graphing calculator to check these. You should be using your graphing calculator all the time, to, get more familiarize yourself with it, to double check your work, to graph these. But it also is helpful to know how to graph these without a graphing calculator, because remember that your graphing calculator is just a tool. You should not become dependent upon it. Right? It's good to check your work with it, but it's good to know how to do this stuff by hand. Yeah, okay, so I think, I don't remember why I was doing all this. We're just going to stop the video right here because I don't know what I was doing. All right, good job, you guys.